Okay, so this is 4.3, the second part. In the first part, we solved for the DE with constant coefficients, where basically A, B, and C are real. And we used the solution, the general solution y equals e to the rx. All we did was take the derivative and the second derivative and plug it into the DE, and we got our auxiliary equation, which we just throw it into the quadratic formula and we solve for it. So this is the third case where the discriminant is negative and we end up with two complex roots. They're always conjugates of each other because it's plus or minus. And I gave you the solution, but if you noticed, I didn't go through anything. And really, with R1 and R2 being written out, our solution first starts off looking like this. And now we're going to show how we end up getting the two real solutions from two complex conjugates. So with R1 being that, e to the R1, alpha plus beta I x is one solution. And I'll go ahead and put a C1 in front of that, write out our general solution, plus C2 e to the alpha minus beta I x is my two solutions that I get from the quadratic formula. And I will show us how we end up with the general solution with two reals. You can see we do use alpha and beta. And what we'll be using to show this is something called Eulers formula. So if you've never seen this, again, it is Eulers, sounds like Oilers. And what Eulers formula is e to the ix is equal to cosine of x plus I sine of x. So what I'm going to do first, before we go anywhere, is prove Euler's formula using some techniques from Calculus 2, from the series. So here's the proof. And it just starts off with the series of e to the x. And hopefully you remember it. If not, I'm going to refresh your brain. It's x to the k all over k factorial, starting at k equals 0 to infinity. And let's go ahead and write that out. For k equals 0, it's x to the 0, which is 1. K 0 factorial is 1. Plus x to the 1 plus x squared all over 2 factorial plus x to the third over 3 factorial. And I think we're going to need one more at least to see the pattern. And we'll have to go dot, dot, dot because it does go to infinity. So there's e to the x, but clearly we want e to the ix. So all I have to do, we could do this in Calc 2, is replace every x that we see with ix. So that's what we'll do, and then we'll clean it up. So that's equal, so e to the ix is going to equal to, instead of x, it's ix k all over k factorial. Okay, so now let's simplify it. This is 1. There's nothing to simplify about these first two terms. Here we'll get I squared x squared, and I squared, if you remember, is minus 1. So that's minus x squared. Again, I squared equals minus 1 by definition. Here we have x to the third, I to the third. I to the third is I times I squared. That I squared is minus 1 times I. So this is minus, didn't mean to touch that. This is minus I. And here, I to the fourth will just be minus 1 times minus 1 because it's I squared. So that's x to the fourth. And then we'll go dot, dot, dot. And let's not forget our 4 factorial, our 3 factorial, and our 2 factorial. We don't need 1 factorial and 0 factorial there. Okay, now what I want to do next is just rearrange, write this as a complex number in standard form, which means we write our reals first. This is a real, this is a real, and this is a real. And then second, we'll write our imaginary parts next. Let's write those, let's rearrange. 1 minus, and then the I terms have an I in common, so I'll factor it out. And probably we can see the next term. So if I group these, I group those, and I did forget to write, this goes on forever. Well, do you recognize what we have? We have an alternating even series and an alternating odd series, and if you remember, this is the series for the even trig function, cosine of x. Not a coincidence that those are even powers. And this is the odd, which is the series for sine of x. So we proved that this is equal to cosine of x plus I sine of x. That's e to the ix. And we're going to keep that box. And we forgot to write our x there. Okay, we'll be using that to prove our cos. So what we're going to do next is, now we have the ability to simplify what I told you our root was. So these were our complex roots. We're going to take this and simplify it using Eulers formula. So we have, using algebra, e to the alpha, e to the beta ix, since alpha x gets distributed. This gets distributed, plus c2 e to the alpha x, ix, sorry. And do you see that we can pull that out? It's in common. And now we can use Eulers on both of these. So let's do that. We'll need a little bit more room. And we are replacing e to the beta ix with two terms. So that becomes cosine of bx, beta x, plus I sine of beta x by Eulers. And the second grouping, same thing, but it has a negative in it. Cosine of minus beta x plus I sine of minus beta x. I'll wrap it since it has a negative. Okay, so next, let's just clean up. We know we can rewrite these without the negative angle. Everything else I'm just going to copy. Since cosine's an even function, that negative angle can just disappear. It's on an even function property. Since sine is an odd function, that negative goes in the front. So what I want to do next is I want to go ahead and distribute all the c's, the c1s and c2s. And that's a c1. Okay, so next we need to write it as a complex number in standard form. We'll combine these. We'll combine the real parts first. So we're adding this plus this. Clearly they're both cosine of beta x, so it's c1 plus c2 of cosine beta x. Plus those both have the I in it. I'll factor it out. c1 minus c2 sine of beta x. Now, this is just some constant. I add two constants, I'll get a different constant. So we can go ahead and just call that c1 again. It's not really the same one, but I like c1 and c2. instead of C3 and C4, just so we have a good counter on it. Remember, this is second order, so we do need to have two constants. So this was y equals. Now we're almost there. It looks a lot closer to what our real solution is, but the problem is we still have an imaginary in here. So before I'm going to circle this so we don't lose track of it. Before I go on, I do want to prove to us something that will help us in this. And basically, here's the statement that I'm going to prove. If I have a complex solution, if u plus vi is a complex solution to the dE, the second order dE, then u and v, which are real, those are the real parts to the complex number, are two real solutions to the dE. Okay? So once I prove this, I've pretty much proved that my solution is this without the I. Okay, because those will be my real part and my second real part. We write it as a linear combination. Okay, so let's prove this. So our proof, well, there's not much way to start, except all we know is u plus vi is a solution to that dE. So we'll call it y equals u plus vi. And we're going to need to plug it in. Well, we'll plug it in, and we can simplify that. You can distribute a distributive across a plus. It's not a power. So that's u prime plus v prime I. And then I'll be plugging in y double prime, which is u plus vi double prime. Which, again, you could take the second derivative across a plus. That's what we're going to be plugging in to this, which is a solution to this. So instead of y prime, I write this. I'll write my dE first. So replace y prime. Well, y double prime. Replace y prime now. Replacing with 2, we do need to put parentheses around it. And y. And that's equal to 0. So let's go ahead and distribute, clean it up a little bit. Okay, so the next thing I want to do is maybe gather up all my u's, and then we'll gather up all my v's. Notice how all my v's have I in them. So basically we'll be writing this as a complex number a plus bi in standard form. This the yellow. Even color coded it for me. And then my second grouping are my V's, and they all have an I in common. So another thing that we have to do, hopefully you've seen this before, we have a complex number on the left, and something plus something I. And so we need to pair this up with a complex number. 0 plus 0i is how we want to look at it. And so what we're going to do is we're going to equate coefficients. This real part must equal to that real part, and this real part must equal to that real part, which is 0. So we'll write that out. And the second one, and oh wow, let's look at our original differential equation. Look at that. Doesn't that look like it has the same form, but instead of a y, it's a u? What does that mean? That means we plugged it in, we got 0. That means u is a solution. And it looks like the same thing happened over here. It is in the same, it fits our original dE. But v, you plug in v and you get 0, that means v is a solution. And u and v are real, because they are the real parts to our complex number. Okay, so we basically proved it. So, which means we have, this is our solution. So this is our solution that we got from plugging in our two complex roots. Therefore, we can take the I out. That and that are both real solutions without the I. Is my real solutions. My real general solution to the homogeneous. These are independent. We can check that, but we have already done a similar check. You can use Wronskian to check it, and therefore, since it's degree 2 independent, that's my general solution. Okay, let's do an example. So our solution, e to the rx, because they are constant coefficients. Take the derivative and the second derivative and just plug those in. So y prime, factor out the e to the rx. Okay, so the 4 and the 5 totally looks like it's going to factor. Please, please, please don't factor it incorrectly. It doesn't factor because this is a plus. In order to make a 4 from a 5, you need the difference of 5, and you would need a plus and a minus. That need to be -5 to work, and it's not. It doesn't factor, and you'll see when we use the quadratic formula. So let's use that. Minus b and minus 4 is 2i. Don't forget to divide 2 into both. And then let's be careful. That's a 4. And that's a square root of 4 is 2i. Just I, or 1i. Okay, so what we have here, alpha is equal to 2, beta is equal to 1. We can just, basically, you really want to just memorize the formula. You could always use de Moivre's theorem to bank it out, to crank it out. It's not hard math, really, and it's kind of fun. But I prefer just complex formula. You have sine and cosine, but don't forget about, you have your e to the, if you have an alpha, you have e. So that's my r. My solution is e to the rx. So y equals c1 e to the 2 plus I x plus c2 e to the 2 minus I x. But like I said, we already have, using Eulers, you can crank it out. You know, first you gotta do some algebra, but you can memorize the formula too. And I think I'm gonna go with just plugging it into the formula. So alpha is 2x, don't forget your x, c1 cosine of beta x, beta is 1, so it's just x, plus c2 sine of x. Done. Okay, so that's all I'm going to do for this video. Stay tuned for the next video, and it is basically a higher order than degree 2, but it's using the same method. And so what you might need a little bit of review on, which I will review, is synthetic division. So stay tuned for that video.